Right.
No mobile phones on.
Sorry?
No mobile phones on.
No, I don't. Yeah. Okay, I suppose that you can hear me now, right? So good afternoon, everyone. My name is Arttu Polojärvi. I come from Aalto University, and then I'm going to talk to you about DEM and modeling ice failure processes with DEM. Maybe this is a little bit more, let's say, ice engineering type of presentation than some of the previous ones. Okay. So there we go. So that's the outline for my presentation. I'm going to say a couple of words about numerical engineering scale ice mechanics, just to get you on the map what type of work I'm doing. Then a few words about the mechanics of the DEM simulations that I'm doing. I think it's worthwhile to kind of have an idea what a discrete element tool in our case means, what type of things there is. Some numerical examples. I'm going to show you that I'm able to validate my model against lab scale experiments. And then I'm going to share some of my thoughts related to the requirements of discrete element modeling in engineering scale. And now this word engineering scale here exists a lot just because, I mean, the interactions and such that I'm doing are sort of, bound on a certain scale, but you hopefully are able to sort of understand that many of these things then can be extended in other scales as well, and extended into other types of problems than what I'm going to present here. So for ice engineer, why would you be interested on doing numerical ice mechanics? So a couple of drivers that are really sort of telling to that or motivating our work these days is that the offshore structures as they are built these days, for example, I think the best example are offshore wind turbines, that they must be very highly optimized or they basically won't get built. And doing experimentation, these type of structures is expensive, even in model scale, and it's very challenging. So basically that then says that, okay, we should probably be able to do something to model these type of structures. And when we do this type of modeling, how we like to do it is just to, not produce a number, but really to understand, let's say, not just produce a number for maximum ice load on a structure, but really understand what is going on in this type of ice loading process. The other driver then, let's say on a more general level, maybe is that the in general the processes related to ice failure are complex, they're not very well understood, and that basically then leads to the fact that the predictive power of some of the ice models might not be what it could be if we understood a little bit better what happens on engineering scale, for example, during bridging and so on. Here's an example of the work that I do often. Here is an offshore wind turbine foundation, which you will see in later slides as well. And there is an ice field moving in this picture towards left and colliding with this structure here. The scale here is so that the structure is about 10 meters. So that gives you on the waterline. So that gives you sort of the idea of the scale that I'm working on in here. In this type of simulations, I would typically have the ice field being maybe 150 meters long and so on, at least to kind of see what is actually happening. Another example that gives you an idea and what we do is here. This is sort of a prototype of SA Agulhas, which many people in this room have been, and it's advancing through an ice flow field. In this case, made from square, very simplified ice flows, just in order to study how ice flow shape affects the ice load on this ship. And one thing to understand here right away is that when we do discrete element simulations, we are doing them in 3D. So it's not like, you're going to have these ice flows just bouncing on one plane around, but they can actually rotate. They can always raft and do things that ice flows are are usually doing. They can slide along the ship hull and so on. So that's something to understand right off the bat, that we are not dealing with 2D simulations here. This is another picture from the same simulation that I just showed you. Gives you an idea on the scales here. So our outflow field here consists of, I can't remember, some tens of thousands of ice flows, and we are studying a situation where Akulhas is now traveling through an ice flow field that is about 2 kilometers long. So that again gives you some idea what we are doing. Of course, you have to understand, okay, the domain here might be 2 kilometers long, but the interactions between the ice flows and the ships are, again, in sort of some meters scale and so on. Okay, but that's about the introduction, and then I thought I talk a little bit about the mechanics and how to model these kind of situations. And maybe I try to, on the same time, highlight a couple of features that I think that are important in modeling ice failure processes in this scale. So if we first start from the sort of the starting point, that the what a model must have. I mean, without these, you won't be able to do any of this kind of modeling. So what you have to be able to do is to describe deformation and continuous failure process of an intact ice sheet. I would say the key word here is continuous failure process. It's not enough to just model, ice sheet fracture once, but you have to be able to run several situations where ice sheet fractures in a simulation. You must be able to then model the motion of the ice fragments that come out from these failure processes, because otherwise you won't be having any ice pile-ups or any ridging or anything like that. And of course, one of the important things and why we use discrete element method is this contact interaction. So that becomes quite important. So you will need to be modeling all the contacts that could exist in your simulations. So let's start from the intact ice sheet. How do we model that? So first of all, I mean, I should probably mention that our discrete elements here are these. Well, what we do is that we take our ice sheet, we use central Voronoi tessellation to tessellate it, and our discrete elements are then the smallest units that you can see here in this type of simulation. We combine those with Timoshenko beams. So basically what we have is a sheet of rigid discrete elements combined by three-dimensional Timoshenko beams. I won't get, they're kind of tedious to get to work, but that's another story, I think. In our case, prior the ice fails, the beams are elastic, but they also have viscous damping. So there's an elastic component related to the strains of those beams, and then there's viscous damping. And without this viscous damping, you will never get this type of model to work. I mean, never. So no reason even trying. Once any of these beams reaches a failure criterion, which is predefined, I will show it to you in a minute, the beam fails. So ice can locally fail in one of these points, one of these joints, or whatever you would call them. And that basically, then leads to a situation where you might get a small crack in your ice sheet, and then it could continue growing. What I don't allow now here in these simulations is the cracks to advance through the discrete elements and so on, but we can then discuss if that is needed or not. Why Timoshenko beams are nice in these kind of situations is that I right away have shear and tensile stresses, or shear and tensile stress components in my beams available, and that's then becomes handy next when you start to look into the ice sheet failure. So our ice sheets, they now fail when the stress state is such that it reaches a failure criterion that we write as in here, and what we in fact use as a yield surface, and that I guess is what to take home from this slide, looks something like this, and it's actually drawn here. The important thing here is that we are using this cohesive softening here. So basically, once we hit a stress state where we then say that, okay, this type of mixed mode failure criterion is fulfilled, basically, we hit that yield surface, we ramp down the stresses in our simulations. So basically, in short, what happens is that we dissipate energy. And that basically happens according to these type of plots that you probably saw in Jukka's presentation on Monday. So you have a crack opening, and as that grows, then the stresses in a given beam are being ramped down. And again, something that, if this would be like a fully elastic failure, then what comes out of that is that your ice sheet is going to basically shatter. It's going to just go into small pieces. And that's something that we learned the hard way in the past, basically. So you need to have some sort of cohesive softening in the model. And I mean, as Jukka showed on Monday in his presentation, then that is actually what you see in nature as well. The ice, there is some kind of viscous or cohesive softening going on. Basically now what I'm using here is this kind of linear softening. I could, of course, go back to Jukka's and Iman's results and make this, let's say, more representative for ice, but this seems to work quite well in our case. Once our ice sheets fail, then we have to start to deal with contacts. And how we deal with contacts is just very, very standard thing for discrete element method. We allow small overlaps, and we calculate our contact forces based on those overlaps. A couple of things to understand here probably is that our load, how it's calculated, it has a normal component and it has a tangential component. And the normal component is what we call elastic viscous plastic, and that's something that I think dates back to Mark Hopkins' work in the 90s. That type of contact force model. And in a tangential direction, there's elastic compliance, damping, and incremental Coulomb friction. So basically, in short, there is contact friction. Why I wanted to include, this is a little bit busy slide, but why I wanted to include this here is that what it describes basically is how we calculate our elastic component for the contact force, and actually how we calculate the other components as well, is that we do very accurate contact resolution. So we solve the contact geometry in a very detailed fashion. There are certain reasons for that, which I don't plan to get into here. But basically, that is pretty much how you have to do it if you want to do it correctly. And not only for the elastic component, so how we calculate the elastic component is basically then as a surface integral over that overlap area, and there is a sort of a, let's say, a little bit laborious way to do it, but it just needs to be done if you want an energy preserving contact force model. The viscous damping then is just basically related to the change in that overlap volume area, and another reason why this overlap volume area needs to be calculated quite accurately is that only then you can, in any way that makes sense, define a plastic limit for your force. So basically, what I do in every contact is that I define a contact area, and then I'm able to say that, okay, that contact, I mean, it has a maximum stress that it can transmit, and that sort of limits the maximum force that the contact can then transmit. And then basically the normal force, it's just a sum of these different kinds of components. In a tangential direction, okay, the story in total is a little bit more complicated than what is presented on this slide. But we have this tangential compliance, so you could take that as elastic force in the tangential direction. Again, you need to have some damping, and then your tangential force is limited by Coulomb friction, and that's pretty much it in short. This thing here takes a little bit more challenging to use in 3 dimensions than what it appears from there, but it's doable. what you see in all of these equations are these contact stiffnesses, KTC and KT and contact stiffnesses and damping parameters. And it's often discussed that, okay, how to then define those. Well, I found a way to at least say that in some simple cases I can pretty accurately define them based on the actual material properties of ice, or material properties that I could measure. I mean, it's obvious that they are estimates in many cases, but I mean, for certain cases, things work quite nicely when you define them like this. The important thing here really is that, okay, that now my contact parameters are in fact functions of actual material parameters, or I can basically define them based on known material parameters. So I would say that it's not anymore exactly a penalty-based method in that sense, that they actually, these stiffnesses, they make physical sense. But yeah, it's a little bit longer story also how to get to these equations. Of course, then I need some external forces as well, and what I have here is basically hydrostatic forces. I have a very simple model for water drag, so I'm not, studying situation where ice moves very fast, and I'm using added mass if needed, basically. And I mean, these are fairly straightforward to calculate, but it's important probably to understand that if you want to use any kind of hydrostatic forces or water drag, you need to do it often by using some sort of surface integrals, and they take a little bit of time to do. You cannot just start adding them on particle centroids, because there's of course going to be torques and so on related to those. Good. I think that's all that I wanted to say about the mechanics, and then I was going to show you a couple of numerical examples what I've been doing with my model. And really, this first thing is a validation study. So inclined structure in lab scale. So I have a structure that makes a 50-degree angle with the horizontal here, and I have an ice sheet moving towards that structure. And basically, what I've done here is to mimic a lab experiment from our Aalto ice and wave tank from 20 years ago, in fact, and that's. Yeah, I mean, that's pretty much, I guess, describes the problem here. And what does my simulation look like? It's basically now, I mean, what you have here is an ice sheet tessellated, and as I described, in some tens of thousands of elements, hitting this, moving towards left, hitting this inclined structure. And what you see is that it's really going through this type of, continuous failure process as I described. Breaking into small pieces. The pieces are piling up, then they are at times submerging into the water and so on. And this is really, I mean, what it looks like when you are in the lab. Unfortunately, I don't have a video of this experiment because, yeah, like I said, it was performed soon 20 years ago, I think. Here is some results. Okay, now it shows a little bit bad but anyways. So what I've done on this slide is I compare the load on that structure, the horizontal load on that structure from my simulations and from my experiment. And what I see is that they show very similar behavior, basically. What you don't now see is, I mean, that's just one simulation, but I ran for this, 9 simulations with different tessellations, different discrete element sizes, and so on. And they all seem to fall quite nicely on top of this experimental data, basically. I mean, you would not expect this fit to be 1-to-1. That would just be suspicious, basically. But what you see is that you have the load that is increasing, it's dropping, it's increasing again and dropping, and so on. And what you have also is that your maximum loads are about on the same level. And both of these load curves are showing sort of an increasing trend in them, and I'm quite happy on this, in fact. And when you change things around a little bit in your simulations, what you have is that your details of your load curve are going to be looking a little bit different, but I mean, these general trends, they remain the same all the time. what happens then in these simulations? Oh, yeah, I should have maybe mentioned that, okay, here what you have on the horizontal line is the amount of ice that has been moving against the structure. So you could think of this as some sort of load time series or load displacement series or record. So what happens in one of these peak loads? I mean, that of course is what interests ice engineer at first always. What happens when you hit a maximum load? I try to illustrate it with couple of snapshots from my simulations. So you start from a situation where you might have some ice rubble against the structure, but it's underwater here. There's no rubble riding up the structure. What you have then is that when your load is increasing, typically you see that the volume of ice riding up the structure is increasing. At maximum load, you usually have a situation where you have quite a bit of rubble against the structure, and then your load drops when the rubble basically sinks. So in a way, it's quite intuitive that would cause high loads, that you basically pile up ice against your structure, and then this ice in fact is eventually going to give up, and things are going to submerge, and then this process starts again. And of course, all the time this rubble pile here is getting bigger, and that basically explains this increasing trend. There is more support to this ice sheet there. And from these simulations I can get the exact rubble volumes and so on, and when I plot those on top of the load curves, I can see that basically there's a 1-2. The correlation factor between those two is basically 1. So they basically, what I'm saying is that this whole thing that I just showed you explains all of these peak forces pretty much very well. A few words on slender structures. I mean, of course, now one could say that maybe that previous example could be modeled in 2D, and it works in fairly, I would say, fairly well. But when your structures start to get slender, like in this case that we have this conical structure, then of course the ice is flowing around the structure as well. And this is something that Mark was talking in 2017 when he was describing his discrete element work. But things actually work quite similarly in this case. So here's again 4 snapshots from a simulation and a load time series from the same simulation. What you see basically is that when your loads are the highest, you have always most of this rubble, or the volume of the rubble riding up the structure having its highest value as well, or highest volume basically. And then things again submerge and so on. But what is actually important then is that you have this clearance effect, that basically all the ice is then moving around the structure, and what you end up seeing is here are results from a couple of simulations with different ice thicknesses, is that you don't have this increasing trend anymore in your data, but basically things flatten out, and you have these sudden drops where you actually have this clearance happening and so on. So that's the type of data that you can get out of these simulations if you're able to run the simulations long enough. So every now and then I see, or you see simulations which been run like, I don't know, few meters of ice and so on, and then you basically miss all these features that are essential for understanding this whole process. So I'm going to finish with a couple of words on model requirements as I see them based on these simulations. So what we've been doing in the past, and what people have been doing in the past a lot, is to model ice loading scenarios or ice failure processes such as ridging and everything in 2 dimensions, and it is really a good question to ask that do we actually need 3-dimensional modeling, or is 2D enough? And then I think that the assumption often is, because, well, okay, if you look on the data from 2D simulations, what you see is that basically when you run many simulations, you get a lot of scatter in your data. My experience on these 3D simulations is that there's quite a bit less scatter, as that one slide where I showed the load record showed, than in 2D simulations. But then the question really is that if we run enough of these 2D simulations, are we going to get some sort of averaging possibility to average things and basically get into same results. And that's something that I don't have an answer at the moment. Maybe more asking that question. I think the essential thing here is that one has to be able to answer that is the mechanics presented correctly, all the mechanical phenomena presented correctly by the 2D model. And I can see that in some cases that's not necessarily the case. In 2D, you get a little bit different types of phenomena happening than in 3D simulations. But like I said, I mean, depends probably on an application. And then, of course, you know, if you want to study these type of structures that I showed, for example, Slender structures or I don't know, islands where you have ice flowing around the island and so on, then of course you need in fact 3D simulations. Other requirements that I kind of saw when doing this work was that like I mentioned, it's not enough to just, you know, model the first few meters of ice structure interaction or first few seconds and so on, but you in fact need to model long periods of time. And something that I did not mention, but has been known since the 90s at least, is that you cannot model these kind of situations by using spheres or circles, circular elements and so on, just because then the interaction process itself changes and the pile-ups change and so on. So where this all leads to, I mean, the requirement for the simulated period, the model size, and using certain kind of shape descriptors for your discrete elements is that you need to be able to build your tools quite fast, or you need to be able to parallelize them. I mean, and that's what we ended up doing. So everything that we are running is basically parallel. Of course, this requirement for simulation domains, I mean, that always depends a little bit on your application. So what I'm interested on here, or what I showed, was that I'm interested on a situation where I have, you know, an infinite ice sheet. But of course, sometimes you might only be interested on smaller ice features. So maybe that's not so limiting in that kind of case. And yeah, and I mean, like I mentioned, then if you want to, you know, use let's say reliably things like plastic limits and things like that related to contact, you need to have your discrete elements described in a way that actually allow you to calculate contact geometries quite accurately and so on, even though that's a little bit painstaking to do sometimes. But I think that I don't have really any other conclusions at the moment, and I'm done with my presentation. There are a couple of papers there that basically describe a lot of this work, and some earlier work that relates to it as well.
Thank you very much, Arttu. Are there any questions? Alberto was the first, I think.
No, quite cool, the simulations. Is the water surface fixed in a sense? Can you put waves and winds on top to drive like the drift of the ice and the motion of the ice?
I would say that if you would do sort of like, it depends how complicated model you would like to have in that sense. So basically, of course, I could define my, you know, kind of the boundary where I have the water. The simplest case would be that I would give it some kind of shape which could change in time, and that would be totally fine. If I would like to fully couple what I'm doing here with some kind of solver that would actually then you know, that your waves would be affected by the discrete elements or the ice sheet, then things would get a little bit more difficult. Does that answer your question a little bit at least?
Thank you. Any more questions?
Yeah, thank you for the talk. That was really interesting. My question would be, so I'm assuming that in these simulations, you need to resolve the elastic waves within the ice sheet between the flows. So what would be the type of time step that you need to resolve that, and the limitations in terms of simulation length that you feel like is realistic?
Yeah. time steps are small. I mean, typically in order of 10 to minus 6, sometimes 10 to minus 5. So yeah, they're small. When you mention elastic waves, yes, I do have to take care that those don't travel over the place, because they would eventually end up breaking my ice sheet. And that's one of the reasons why you need to have some sort of damping in your model always. And that's of course a thing that is very difficult to in fact measure what kind of damping I should use. But if I don't do that, then I'm just going to have stress wave traveling all around the place, and you know, whatever time step I would use, they would eventually end up breaking the ice sheet, I think. But yeah, time steps are small, definitely. Yeah.
Any more questions?
Oh, thanks for your talk. What are the next steps that you would like to improve in your model? What the next functionalities?
What I'm working on, or what we are working on now, is basically getting a little bit more kick out of our code and just getting even higher resolution and maybe bigger domains and so on. That's something that we want to do. What I don't know, like let's say ice structure interaction wise, what I would like to do next is to study a situation where I have, you know, several structures might be actually quite far from each other, and see then how the ensemble of structures behaves in ice. And then of course, you know, you need larger domains and so on. But yeah, that's sort of what we want to do next.
Really nice talk. Thank you very much. At first you showed a picture where there was a ship with some flows.
Yeah.
And I was wondering if there was any other experiment and what were the initial conditions, because there seems to be a ship wake, but you said that you need to prescribe like a profile for your surface. So how did you do that?
I didn't. I mean, yeah. So first of all, yes, there are observations. So those come from Agulhas, basically, and there are observations. What we compared was the ice loads on that ship, basically, as measured on the field. What we see is that they get, I mean, we get reasonable estimates on those loads from reasonable predictions from our simulations. But again, yeah, I'm not, you know, I don't have any waves in my simulations in that sense. The ship would produce waves and then things would happen. So it's sort of rudimentary in that sense. But still, you get quite good predictions, I would say.
One last question might be.
In your model, you used hexagon elements, yes?
Most of them are hexagons, probably, yeah. But I'm not restricted to those. What I want to do is just basically use centroidal Voronoi tessellation, and where it leads to is that most of the elements are hexagonal, but there might be also other shapes as well.
Did you investigate other shape?
Did I investigate? No, well, let's say that we did not really investigate any other shape, in a sense that you know, we only have been using these kind of tessellations because we know from the past that it actually behaves quite well in these kind of situations. I think it's a fairly standard way of dealing with this, because then you have, you know, some properties of cellular solids and so on, which you can at least compare your model to, because then that's another story than how to start, you know, thinking of parametrization of this ice sheet and so on when you use an approach like this. But that's another, yeah, a longer story.
Many thanks.
Thank you.
Thank you, Arttu.
Thank you.
Let us thank both speakers once more.
Just to remind again that the discussion session tomorrow is cancelled, but it's not cancelled for today. So after coffee, during the afternoon tea, please return to this office to discuss kind of future of research in some sense, or everything what you want to speak about, all presentation today and yesterday. So see you after the break.